Talking about AC machines essentially means going back to DC machines. I tried to point it out last time also. Anytime you have rotation involved in generating electricity, you essentially get AC signals. For DC generators, what we did was we put a component called commutator to rectify the signal and get DC out of it. Now, when we are trying to go back to AC machines, obviously we don't need commutator. Okay. Now, other problem is that AC machines, whether generators or motors, are typically going to handle large powers. That's the reality. Let's talk about AC generators to begin with. I'm going to repeat myself a bit here. Let's talk about AC generators a little bit. They can be single phase and three phase. That's another story. Now, if you take the traditional DC generator and remove commutator and measure the output, you'll get AC output. That's single phase output. Okay. Assuming that you are supplying mechanical energy by rotating the shaft. And you will have brushes connected to rotating armature, picking up the voltages. The thing is, when powers become high, that means voltages become high, the conductors which are rotating will have to carry very high currents, and that becomes very dangerous. So as I pointed out last time, what we do in such cases is we reverse the role of conductors and magnetic poles. We make magnetic poles rotating and make conductors stationary. That means we move all the armature circuitry, that means all the conductors, to the stator, and we put all the magnetic poles on the rotor. Faraday law doesn't care as long as you have relative motion between magnetic field and current carrying conductors. So that is the essential difference when it comes to AC generators. On top of it, the windings on the stator can be three phase or single phase. That's another way of classifying AC generators. The word that we normally use for AC generators in industry is alternator. Other problem with this approach is that you still need to excite the magnetic poles on the rotor using a DC input, which is generally done using a small DC generator. So this can be done. It is done actually in a lot of cases. And this kind of construction is known as synchronous construction, because this works only when the rotor is rotating at a particular speed, for which I have given you formula last time. The other approach in which we remove this DC input requirement is, especially for motors, that we short circuit all the conductors on the rotor. Rather than producing magnetic poles there, we short circuit all the conductors. I'll show that in detail later. And that leads to a second variety of AC motors called asynchronous motors or induction motors, where DC input to the rotor is not necessary. With all that in mind, I want you to look at this small PPT prepared by one of the faculty members in the mechanical engineering department of LNM IIT. He has actually looked at mechanical side more than the electrical side, which is fine. That's the entire nature of this course anyway. Induction motor is an asynchronous motor. There is no DC input required to the rotor. Instead, all the conductors on the rotor are short-circuited, and that produces a transformer-like effect. I'll go into theory a little bit later in detail, but for now, just take the construction aspects in mind. The stator, whether you're talking about asynchronous motor or synchronous motor, the stator is more or less the same. It is the rotor where the construction becomes very different. The stator has a steel frame which has a cylindrical core, and you use laminations of silicon steel because that reduces losses. Silicon steel has lower hysteresis loss. Laminations make the eddy current loss lower. This is similar to what we saw in transformers. Slots are there on the stator to put the three-phase winding or single-phase winding. In this particular case, we are talking three-phase, so there will be three-phase windings, which will be either delta or Y. Conductors need to be insulated, of course, so that they are not touching metal anywhere. Rotor is essentially a hollow laminated core having slots on its outer periphery. In case of induction motor, we short circuit all the conductors on the rotor to produce the effect of induction. Okay. By the way, single phase version of induction motor is what we are using in our ceiling fans all the time. The construction that we use is known as squirrel cage construction. Instead of having thin conductors on the rotor, we make them solid aluminum bars, as shown in this diagram on the right hand side of this slide. And this is a very rugged construction. These fans can fall even 40 feet and still the damage done will be very small. Okay. So squirrel cage is actually a kind of name given jokingly by somebody. This construction looks like you have caught a squirrel in a cage and the squirrel now cannot get out. So this is a funny name, but it has caught up. Even in the books, they are using this word, squirrel cage construction. Wound construction is another story. I'll come to all that detail. But important thing that I want you to remember is that we are looking at two different types of machines as far as AC is concerned. One is the induction type, the other is the synchronous type. Okay. Rotor, instead of squirrel cage construction, can have regular thin wires running also. That has its own advantages. In many cases, you want that rather than the squirrel cage construction, especially if the speed is going to be very high, then squirrel cage construction starts having mechanical problems. So in that case, wound rotor is a better solution. We'll come to principle of operation later also. So I want you to be aware. There's a very interesting term coined for induction motors. Induction motors do not run at a constant speed, but they begin with synchronous speed, which is given by the well-known equation that I have shown last time and I'll show again soon. As motor picks up the speed, as motor is loaded, its speed is going to be slightly lower because of the load. The difference between synchronous speed and actual speed divided by synchronous speed and the entire thing multiplied by 100 is known as slip. Percentage slip is the right word. The smaller the slip, the happier you are. So 5 to 10% slip is permitted in most of the practical applications. Starting is a problem always, especially with synchronous motors. So there are various methods of starting. I'll be going through all of them in detail later. I want you to be aware that starting is an issue. For DC motors also it was an issue, and we came up with unique solutions. Here also there are unique solutions, but when I go to induction motor, I'll talk about it in detail. Single phase induction motor is what we are using in the ceiling fans. Same principle, squirrel cage rotor, but the stator has only single phase winding on it. Again, we'll be talking about it in detail a little bit later. I'll explain this theory later, double field revolving theory. Single phase induction motor, by the way, is a self-starting motor. using some innovations, we have been able to make it self-starting. You don't need to give any mechanical push to get it going. I'll talk about that a little later. Okay. And our single-phase series motor, we'll talk about it later if time permits. There's a lot of special motors in market right now. Compensating winding, I'll come to all that later. Synchronous generator is the opposite of synchronous motors, and this is the one that we call alternator. I have been talking about it a lot. I'll be talking about it a lot anyway. So essential idea is that it operates only when the rotor is at synchronous speed. I told you last time that depending on the speed of the rotor, you can have either salient pole rotor or cylindrical type of rotor. In cylindrical rotor, we use electromagnetic techniques to create magnetic poles. While for salient pole machines, we actually have physically visible poles, bolted or welded to the construction. I think I've explained the principle of operation a lot. Synchronous motor is the opposite of synchronous generator. It operates only at a constant speed. And it also needs a DC input. That is one disadvantage. We'll come to methods of starting later. So this small PPT, I'm going to share it with you. Keep it for your records in future. Now let's get back to synchronous generator or alternator little bit mathematically now. Let me try to show you a few numerical problems related to synchronous generators. Look at question 1 carefully. It actually has nothing to do with synchronous generator. This is testing your understanding of AC signals. But this problem appears even in GATE exams. What is the equation of a 25 cycle voltage sine wave having an RMS value of 30 volt RMS? What is the value of this voltage when the time is 0.005 second? What fraction of a cycle has the wave gone through in 0.005 second? Assume that the wave crosses the time axis in a positive direction when the time is equal to 0. So your objective is to create the equation that describes this particular voltage signal in time domain. First of all, the RMS value is given as 30 volt. So peak value will be 30 multiplied by square root of 2. Simple enough, right? It's a 25 cycle signal. So omega will be 2 pi multiplied by 25 radian per second. That much is clear, right? Let me show you the solution. F is 25 cycles per second. VRMS is 30 volts. So Vmax or VM if you want is 30 multiplied by square root of 2, which is 42.42 something volts. Omega is 2 pi F, which is 50 pi radian per second, which is 157.08 radian per second. So the equation should be peak value 42.4264 sine of omega t, where t is measured in seconds. It's a sinusoidal voltage, sine wave. Yeah, so we will use sine function. Now, one thing that's given at the end of the question is assume that the wave crosses the time axis in a positive direction when the time is equal to 0. That means at t equal to 0, the wave should be moving in the positive direction. If you take t equal to 0 and t equal to slightly larger than 0, then the value, obviously value at t equal to 0 is 0, but the value as t equal to 0 plus some small number should be positive. That's what they're trying to tell you. And that I think is being satisfied by the proposed equation. At small t equal to 0, small v will be 0. If you take small t equal to some other number, very small number, you will see that a positive number will come out from the equation. So the voltage is actually rising with time when you are crossing time equal to 0 value on the axis. They also want a few other things. What is the value of this voltage when the time is 0.005 seconds? So you simply put small t equal to 0.005 in the proposed equation. Do the calculation, you get the answer as 30 volt. I hope my calculations are correct. One more question they're asking is, what fraction of a cycle has the wave gone through in 0.005 seconds? Frequency is 25 hertz or 25 cycles per second. So time period will be 1 upon 25 seconds, right? Second rather. 1 upon 25 is the full time period. What fraction of that full time period is 0.005 seconds? That is the correct answer. Time period is 1 upon f, which is 0.04 second. And in 0.005 second, the fraction of the cycle that you have completed is 0.005 divided by 0.04, which is 1/8 of the cycle. That's the answer. At small t equal to 0.005 second, we have completed the wave has completed 1/8 of the cycle. Okay. Second question is similar to the first question, but now they want that the wave should go in the negative direction at time equal to 0. So what happens is you put a minus sign before 42.4264 and you get the next answer. That's it. Because now you will see that at small t equal to 0 and small t equal to slightly bigger than 0, the wave will actually travel in the negative direction. So that's the correct answer for this. And other calculations can be made very easily. Instead of plus, we are getting minus 30 volt now. The completion at small t equal to 0.005 is still 1/8 of the entire cycle. That doesn't change. Next problem is even simpler. And this is related to generator. In fact, not one, there are many problems. A 60 cycle alternator has 2 poles. What is the speed of the alternator? This question is asked even in the job interviews. Even mechanical engineers are supposed to know the answer to this. F equal to NP divided by 120 is the equation. F is given as 60 cycle per second. P is given as 2. So calculate N, speed in RPM. I've done that. $60 equal to 2N divided by 20. Or other way around, if you want, N equal to 120 F by P. So put the values. The answer is 3600 RPM. Straightforward answer. Question 3 is done. Question 4. A 60 cycle alternator has a speed of 120 RPM. How many poles has it got? Okay, same equation, but different way of using it. Number of poles has to be calculated. Plug in the values, you get 60 poles. 60. Double check my calculations. Hopefully, I didn't make a mistake. Next one is an AC generator has 6 poles and operates at 1200 RPM. What frequency does it generate? Simply NP by 120. So 1200 into 6 divided by 120, whatever is the answer. At what speed must the generator operate to develop 25 cycles and 50 cycles? So it is basically applying the same equation in several different manners. Question 5, answers are given right here. I'm sure you'll be able to get them. Okay. And the last question, how many poles are there in a generator that operates at a speed of 240 RPM and develops a frequency of 60 cycles? Again, same equation. N is given as 240 RPM, F is 60 cycles. Plug in the values, you get number of poles as 30. Okay, as simple as that. Okay, this problem 7 and problem 8. For now, we will ignore it, but if necessary, I'll come back to it later. Okay. Now, other set of solved problems that I have got for you actually need a bit of theory before we can tackle the problems. As usual, engineers need an equivalent circuit to predict the performance of a given AC generator. For DC generators, we did the same thing. Here also, same requirement. Figure out a reasonably accurate equivalent circuit of an AC generator. I have written the fundamentals of construction once again in the beginning of this document. What happens in an AC generator or alternator, if you want? The rotor has poles. They need to be fed using DC current. Rotor rotates, the poles produce a rotating flux, which cuts the static winding on the stator and produce the voltage and produces the voltage. So magnetic flux produced, let's call it phi F. Phi F induces something called a back EMF. Again, in AC machines also we use that word. This is the open circuit voltage that you'll get out of the generator. And now rather than calling it EB, I'm calling it EG because that is what most of the books use for back EMF in an AC generator. So rotating flux cutting the stationary conductors on the stator produce a back EMF, which I am going to denote by EG. And let's assume three-phase generator for now. Now, if you connect a load across the three, which are known as armature windings, armature is the part of the construction that produces the required electrical signal. So if you connect a load across the three-phase windings, some current will be established. Let's call that IA, armature current, as we were calling in DC generators also. Okay. Our objective is to figure out a reasonably accurate equivalent circuit for describing the behavior of a three-phase AC generator. Now, unfortunately, IA is very large and it also produces its own flux, which affects the flux produced by the magnetic poles. This is a very undesirable phenomenon. Even in DC generators, it is there. I simply ignored it there. I didn't even talk about it. But for AC generators, because constructions usually are large, this is much more serious. This effect is known as armature reaction. It essentially reduces the main flux being produced by the poles on the rotor to a certain extent. If the machine is small, then maybe armature reaction is negligible, but because the armature current will not be too large. But for real life AC machines, IA is generally large, and you cannot ignore armature reaction. You have to account for it in the equivalent circuit. Engineer's job is to capture reality on paper with as much accuracy as possible. We don't believe in deriving equations for the sake of deriving equations. Okay. So we are trying to capture reality. The back EMF will be modified because of armature reaction by some value which we call EAR. Okay. There's a lot of electromagnetism behind all this. I'm avoiding all that. I'm giving you the practical realities, right? By the way, EG and EAR both are complex numbers in general. These are AC circuits here. E resultant will be also a complex number. Now, the analysis of three-phase AC generators is normally done on a single phase basis, because you know the other phases are out by 120 degree or 240 degrees. So if you can model one phase accurately and assuming balanced system, you can predict the performance of other phases with reasonable amount of accuracy. So typically, we draw the equivalent circuit of a three-phase generator based on a single phase situation. And this is how we draw it. It is based on common sense. Back EMF, EG, which can include armature reaction if necessary. But normally what they propose is that, let me come to it systematically. What they do is, instead of adding a resultant voltage, or instead of adding EAR to EG, they try to include the effect of armature reaction by letting EG remain as it is. And in the reactance of the armature winding, they add a fictitious reactance to account for the effect of armature reaction. XAR actually is a hypothetical parameter, while XA is the actual inductance, is representing the actual inductance of the stator windings. XAR is modeled theoretically as well as experimentally, but as far as you are concerned, this value will be given to you. So in the equivalent circuit, we show the reactance produced by the armature winding plus reactance produced by the armature reaction plus resistance produced by the armature winding, single phase. So the back EMF will see these effects before it is going to appear as the output voltage VT. I'm using the word VT now rather than V for describing the output voltage or terminal voltage. Okay. The excitation of rotors, excitation of poles on the rotor is described separately on the left side. Okay. There's a lot of mathematics in terms of how coupling happens between rotating flux and the stationary armature conductors, but I'm avoiding all that for now. So this is the equivalent circuit we will use for approximately capturing the reality in a three-phase AC generator. XAR is the reactance due to armature reaction, will be given to you. XA is the reactance due to the armature winding. You may be given inductance, so you will have to do 2 pi FL calculation to get this value. Resistance of the armature winding will be given to you. Normally, these values are high enough because we are dealing with very large construction in the armature. Now, once you agree to using this equivalent circuit, you have to use simple AC circuit theory to figure out the performance. Terminal voltage will be EG or EA, whatever you want to call the back EMF, minus IA into RA minus JXA IA minus JXAR IA. Kirchhoff's voltage law. What we normally do is we lump the two reactances together in a single parameter called synchronous reactance, XS, which is XA plus XAR. In fact, in numerical problems, you will be given XS directly rather than giving XA and XAR independently most of the time. So equation that you would actually be using to calculate the output voltage will be equation 3. Now, these are all complex values. VT is complex, EA is complex, RA, of course, is not complex. but IA can be a complex number. XS is a complex number. So in general, you will see that there is a phase shift also between EA and VT. And that phase shift is known as power angle of the generator. It is also known as load angle, torque angle in case of motors, and so on. Now, one numerical example based on this equivalent circuit. A 3-5, that means three phase, 5 kVA. This is the rating on the nameplate of the generator. 208 volt, 4 pole, 60 hertz, star connected, synchronous generator has negligible stator winding resistance. That means RA is 0. And synchronous reactance XS is given directly here. It is 8 ohm per phase. Obviously, we are talking per phase at rated terminal voltage. Determine the excitation voltage. That is the word they are using for EA. I am calling it back EMF. They are calling it excitation voltage. Power angle. That means delta. When the generator is delivering rated kVA at 0.8 power factor. This is an AC machine. You need to know power factor of the load also. And the nature of power factor is also given as lagging. That means load current will be lagging the load voltage by a certain angle. Draw the phasor diagram for this condition. First thing is write the equivalent circuit, single phase. EA followed by RA, which is 0, and XAR and XA total is given as XS. So equivalent circuit is quite simple. EA and a reactance of 8 ohm. That's it. Once you have drawn the equivalent circuit, now it's a matter of calculating things. First of all, the rating is always given in terms of line voltages. It's a three-phase generator. So you have to calculate the phase voltage first. We are talking magnitude right now. It says a star connection. So line voltage divided by square root of 3 will give you phase voltage. We have done that in three-phase circuits. So 208 volt divided by square root of 3 gives you approximately 120 volt terminal voltage per phase. And by default, these are RMS values. Armature current at rated voltage will be governed by kVA rating and the power factor. (5,000 kVA divided by, just 1 minute. Yeah, there is a formula for the kVA. You may not recall it, but there was a formula for kVA which was square root of 3 VL IL. If you go back to three-phase circuit notes, you'll see a formula for the total kVA coming out of the three-phase system. It is square root of 3 VLL multiplied by IL or IL magnitudes. IL is IA. It's a star system. So I'm using that formula here to calculate the line current, which is same as phase current in star connection. So if I use that formula, I get 13.88 amperes. This is magnitude, by the way. Now, power factor angle delta is cos inverse of 0.8, which can be calculated as, it's a lagging power factor, so current has to lag the voltage by this angle. This angle value turns out to be 36.87 degrees. You can do the calculation. Cos inverse of 0.8 will be 36.87 degrees approximately. So if we assume that terminal voltage has zero phase, that means that's the reference phase, the excitation voltage or back EMF will have to be calculated using this equation, equation 3. Remember, RA is 0. So VT plus JXSIA will give you EA. That's what I'm doing here. I'm assuming that 120 volt is at 0 degree phase shift. I'm assuming that that's the reference voltage for calculation. So then I plug in the values, 120 plus 13.88 ampere magnitude, and the angle is minus 36.87 degrees. And excess is J8 ohm, which means, J8 ohm, which means 8 with an angle of 90 degrees. You have to be very careful here when doing calculations. So if I take it further, 120 remains as it is, 13.88 gets multiplied by 8, and the two angles add. I'm doing multiplication in polar form right now. So the result is 13.88 into 8, and the angle is 53.13 degrees. I convert this polar value into rectangular value. So I get 66.624 plus J88.832 volts. To that I add 120 volts. I get the back EMF as 186.624 plus J88.832 volt. Double check my calculations. I can convert it back into polar form again. I get 206.69 volts with a phase angle of 25.45 degrees. So torque angle, or let's say power angle for now, power angle is actually 25.45 degrees. The important thing about the operation of synchronous generators is that as load changes, IA magnitude and IA phase changes. So delta value also keeps changing. The phase shift between VT and EA keeps changing depending on the load to adjust to the latest situation. That's how these kind of generators keep producing the required current and voltage. Okay. Phasor diagram, I think you can draw yourself. I have not done it. Now, the last problem, no, not last, the second one is, for the generator in problem 1, calculate the percentage voltage regulation. That should be simple. At no load, the magnitude of the output voltage will be same as magnitude of the excitation voltage or back EMF, because no current is flowing. So 206.69 is the no load voltage. Full load voltage is 120 volt. We are talking per phase. Divided by 120, and then multiply the result by 100. That's a very bad voltage regulation, 72%. But anyway, that's the way it is. And by the way, I should have mentioned, I forgot, that this voltage regulation has been measured at 0.8 power factor lagging. For AC generators, giving voltage regulation value without power factor is not correct. You have to mention at what power factor this value was measured. So the correct answer is 72% at a power factor of 0.8 lagging. Okay. Then the last problem for today is repeat problem 1, assuming leading power factor. So what will happen is you will repeat the calculations in the same manner, but now the phase angle, or rather the whatever you want to call load angle or power angle, instead of being minus 36.87 degrees, it will now become plus 36.87. We have to repeat the calculation with that change. So now what happens is I get back EMF as 103.63 volts with a load angle of 59 degrees. Now this is weird. At no load, I'll see only 103.63 volts, while at full load, I'll see 120 volts. That is the last problem here. I hope you can tackle problem 3 yourself after I send you the document. But problem 4 is even more interesting. For the generator in problem 3, calculate the percentage voltage regulation. Now no load voltage is lower than full load voltage. This is a very interesting phenomenon for AC generators. That open circuit voltage may be lower than full load voltage. We are talking magnitudes, of course. This happens in real life. So voltage regulation now is minus something. This is a very important thing for you to remember, that for AC machines, for AC generators, voltage regulation can be both plus and minus. For leading power factor of the load, no load voltage is lesser than the full load voltage. It is experimentally observed also. While for lagging power factors, no load voltage is higher than full load voltage. I'll show you a diagram next time to describe the qualitative nature of how load affects the voltage regulation.